Coordinate transforms in computer vision and robotics are an integral part for any project or any problem that you're trying to solve. And oftentimes when you are dealing with multiple sensors, multiple different sensor modalities, multiple different sensor installed on a robot, you will have to perform coordinate transforms. You'll have to transform from one coordinate system to the other. Say for example you have a LiDAR camera, you'll have to go from LiDAR frame to the camera frame, and oftentimes this gets very confusing. Oftentimes folks find it hard to understand how to interpret coordinate transforms, how to interpret different coordinate systems. And this was the case with me as well. At some point it was kind of confusing for me to transform from one frame to the other, but then over time I learned my way through it, and in this video I'm going to talk about coordinate transforms in computer vision and robotics and give you some simple examples and use cases to help you understand. Welcome back to the channel, guys. My name is Dhruv, and at Convolve AI we assist small, medium, large enterprises with their computer visions and robotics related problems. If you want to chat, if you have questions, here is the contact information. Feel free to contact us and we would be happy to chat with you. Alright guys, so here on the screen I have created a sample notebook to tell you about coordinate transforms, how they work. So let's first of all start with motivation, right? Why do we want to learn about coordinate transforms? Why are they important? So here you can see on the screen, for example, this is the car setup for an autonomous vehicle. This comes from a dataset called PandaSet, and you can see that for each sensor there is a camera, there is a back camera, there is an IMU, there is a LiDAR sensor here, left camera, front left. For each sensor you can see that there is a different coordinate system that has been defined, right? So here for example for the camera you can see Z is in the front, Y is on the right, and X is on the right and Y is going down. So it's basically, if this is your camera, X is to the right, Y is going down and Z is in the front. That's how the coordinate frame for this camera is defined. For the LiDAR you have Y to the back, X to the right and Z pointing upwards. So it's something like this, where this is X, this is Z and this is Y. And this is your LiDAR scanner, right? So LiDAR has its own coordinate frame, camera has its own coordinate frame, and that's where these coordinate transformations become very important. Another example, let me give you the example from Kitty dataset, right? So this is a Kitty vehicle, data collection vehicle for the Kitty dataset that they used. And over here as well you can see the Velodyne, which is the LiDAR, has its own coordinate convention, and then the camera has its own coordinate convention. So mostly cameras, for example here I'll show, follow OpenCV or OpenGL camera coordinates. OpenCV is X to the right, Z to the front and Y at the bottom, and then on the other hand OpenGL is Z at the back, X to the right and Y at the top, right? So these are just camera conventions. There is no right or wrong here. That's just how these things have been set up. They are defined and accordingly the data is captured and further algorithms are developed. Now let me give you another example. For example, say you have a LiDAR scanner, and this LiDAR scanner, say for example, let me take this as an example, right? Say this is a LiDAR scanner, right? And this LiDAR scanner is scanning points, 360 points, right? So every point will have X and Y coordinate associated with that particular point, right? Now all that data will be captured in that particular LiDAR's local coordinate frame. So as an example, if we take the example of this setup wherein the Y is pointing backwards, X is pointing to the right, to the left, and Z is pointing upwards, this is the convention that will be followed, right? So as an example, if a point is in the front, you will see that it will have a negative Y, say if it's here, a positive X and a positive Z, right? So accordingly you have captured, but now you have captured this point cloud in the LiDAR frame, but you want to convert this into the world frame, right? So say the world frame is defined as something like this, wherein you have the X you have the y and you have the z, right? The usual Cartesian coordinate system. And now you want to get this xy for a point captured from your LiDAR in the world frame. That's where a coordinate transformation is required. That's where you need to transform a point in your particular frame of reference, in the LiDAR frame, to your world frame or whatever frame you want to go, right? That's where this video comes in. So let's go over this tutorial here, and hopefully this can help you understand, right? So I have taken two cases here. The first case is the camera and LiDAR. So we are considering convert from LiDAR to camera frame, basically, to get a transformation and to basically go from the LiDAR coordinate frame to camera coordinate frame. So the first case is camera and LiDAR have the same orientation, where x is right, y is down, z is front. So this is the OpenCV coordinate convention, but they are shifted by 1 meter. So for example, in this setup, assume that they had the same coordinate frame, same coordinate axes convention, but they were shifted by 1 meter in the z axis. So for example, this is your LiDAR and then this is your camera, and the distance between the two is 1 meter. This is how you can define the pose matrix for this particular setup, right? So if you're not familiar with pose matrices, here let's see what a 4x4 pose matrix means. So the first 3x3, so these three numbers, 3 numbers here, 3 numbers here, and these 3 numbers. So here first 3x3 is the rotation. So here this is the rotation part, and then the rightmost column, first 3 elements correspond to rotation. So for to translation in the world, or for that particular pose. So translation camera in LiDAR will be camera in LiDAR. So you take the full pose matrix and you just consider the first 3 elements of the last one. So here let's see, typo, 001, right? So this 001 basically is defining the translation. That is, as we said, right, 1 meter shift in the z. So you can see that there is a difference, 1 meter value for the z part here, which defines that 1 meter shift in the z coordinate. So we define a random some pose for LiDAR in the world, which is as per the world frame, the LiDAR is rotation is identity, and then translation is 542. And then we have the camera in the LiDAR frame, which we defined here, right? So locally they have the same rotation, but they're shifted. Now I want to obtain the coordinates, or I want to obtain the pose of the camera in the world frame, right? So now I have the pose of the LiDAR in the world frame. Let me pull up a PowerPoint slide here. And let's draw this out. All right, so we have the transform from LiDAR to the world, right? This is how we usually write it down. And then we have the transform from camera to the LiDAR. So we have defined these two transforms. Now if we want to obtain transform for camera to the world, this is what we want. All we do is we multiply these two together. So it's a matrix multiplication. This matrix, which is the pose of LiDAR in the world, and then camera in the LiDAR frame, and you will get this particular output, which is the transformation for the camera in the world frame. So if we go here, this is what I do. So this @ is a way in NumPy or in Python to multiply two numpy array matrices, which represent this is essentially doing matrix multiplication of these two matrices. So the first matrix is LiDAR pose in world, and then the second matrix is camera in LiDAR, right? So what we've done is we've just done a matrix multiplication and we've obtained this, right? So you can see that LiDAR in world is 542 and the camera in world comes out to be 543, right? Now this is pretty straightforward here because the rotation with camera and LiDAR was identity, so that stays the same, but then the translation, there is a difference of 1 meter. So hence you can see in the world frame camera shows up as 543 instead of 542 because of that shift of 1 meter in the z-axis. Okay. Now the case 2 over here, the example case is that camera and LiDAR have different orientation. Camera X is to the right, Y is down, Z is front, so same open CV. And for the LiDAR, X is on the right, Y is front, and Z is top, right? So for the camera, this is your Y, this is your X, this is your Z. But for the LiDAR, this is your X, this is your Y, and this is your Z. So Z is pointing upwards, Y is forward. So for this case, if you were to define the transformation matrix between camera and LiDAR, you'll see this is the rotation matrix you get. Essentially, the camera is like this and the LiDAR is like this, so they are rotated by 90 degree around the x-axis. So this is the rotation matrix, and then we've kept the translation same, which is 1 meter in the z-axis, right? And then similarly, camera in world can be computed with the same formulation, and you'll see that the rotation comes in here for the camera. So it is updated as per the camera's rotation with respect to LiDAR, and then again the translation changes to from 542 to 543. So this is our setup and example on how to go from one frame to the other. In the next part of this video, I am going to show you how you can take, say, a LiDAR point and take it from the LiDAR frame to the camera frame, just as an example. So let's go over that. All right, guys. So for the next part here, we are going to go over how you can take a point, for example, in the LiDAR frame, and how you can transform that to another frame of reference. For example, in this case, we are going to transform from a point in the LiDAR frame to the LiDAR point in the camera frame. So if it's confusing for you, think about this, right? You have a LiDAR over here, right? You have this LiDAR which has recorded a point over here, and then you have a camera here, right? You want to know what is this point with respect to this camera's coordinate frame. So this camera's local coordinate frame is somewhere over here. That's where the 000 of the camera is, and you want to know where this particular point is with respect to the camera, and that's what we are going to see how to do it in code and how to do it mathematically. So I just take a simple sample point in the LiDAR frame, which is 1, 2, and 3, just a normal XYZ point. So this step over here, converting to homogeneous, is done because you're multiplying a 4x4 pose matrix with you can't multiply a 4x4 matrix with a point or a vector of length 3. You have to make it homogeneous. So this is a common practice. With homogeneous coordinates, you add a 1 at the end to be able to multiply a 4x4 with a vector. Again, if you are new to homogeneous coordinates, there's a lot of content out there on homogeneous coordinates. You should refer to that, and it's very important. It's like something that's used almost every time in computer vision and robotics, of course. So then for the case 1, we see that the camera and the LiDAR, they have identity rotation, so they are in the frame is the same. It's just that they're shifted in the z-axis by 1 meter. So here we have camera and LiDAR. So what we do is we compute This pose is defining the pose of camera in LiDAR. So if I were to write it down, let me just show it here. So this was showing the camera in the LiDAR frame, right? And if we want to go from this to the LiDAR in the camera frame, right? If we want to do that, all we need to do is take an inverse for this particular pose, right? So what we're doing here is we are converting the we're going we're obtaining the transformation matrix for LiDAR in the camera frame from camera in the LiDAR frame. So what we do is just take the inverse of that pose matrix, and that's what we get. So let me just print out and show you guys what it looks, just in case if you're interested. This is what it looks like when you take the inverse of this particular matrix. So now once we have obtained this particular thing, why did we do this? Because our point is over here, this point is in the LiDAR frame, right? So this point has been recorded in the LiDAR frame, and we want to get this point in the camera frame. We want to know what it looks like in the camera frame. So what we do is we take this point, we multiply this point with the transformation from LiDAR to camera. So here this guy, usually this is how you can see it, they need to be the same, like we did here in the previous example, wherein this guy are same, and what you are left with is this and this, right, at the end, which corresponds to the output here. Now similarly, this and this basically need to be the same, and then you are gonna get the point in the camera frame. So here to obtain that point in the camera frame, what we do is we take the LiDAR in camera, which is this guy here, and we multiply it by this guy here, point in the LiDAR frame. We just take the transpose because just because this is our 4x4 matrix, right, for pose, right, and then we want the vector to be of the length 4. So we take the transpose of that because an array is just 1 by 4. So we take the transpose, so it becomes 4 by 1, and that way we can do the multiplication. And here we print. So again, after you do the multiplication with homogeneous coordinates, the last number is always going to be the ones, is always going to be 1. So you just take the first 3 elements of that output array, that is the point that you're looking for. So point in the camera frame comes out to be 1 to 2. So let's look at it practically, right? So what we had is we had a LiDAR and we had a camera, right? Both of them had the same rotation with their coordinate system. So the orientation of the coordinate system was same. It's just that for your camera it was shifted by 1 meter in the z axis. Now practically, if you think about it, with respect to this LiDAR, a point was at 1, 2 and 3, right? Say it was somewhere here, and the camera, which is shifted by 1 meter, for that x will stay the same, y will stay the same, 1, 2, and z will change because there is a shift in the z. So because now the camera is ahead of the LiDAR by 1 meter, we would expect z to go down by 1, and hence that's what we've seen here, right? So it makes sense. For case number 2, let's go to the case number 2. Here we see that as we had said before, just to recap, the camera frame is like this, x, y, z, and the LiDAR frame is like this, and the camera is in front of the LiDAR in the z direction by 1 meter, right? So same setup, but the orientation of the axes for the coordinate frame is different. All right guys, so for case number 2, where we define our camera to be oriented x on the right, y downwards, and z in the front, and the LiDAR is x to the right, z is on the top, and y in the front, and our camera particularly is shifted by 1 meter in the z of the LiDAR with respect to the LiDAR. So for example, if this is your LiDAR sensor, the camera is up here at a distance of 1 meter in the z axis. Now for a point in the LiDAR's coordinate frame, 1, 2, 3 is somewhere here, right? Positive x, value of 2 for y, and a value of 3 for z. So it's somewhere here in the front. Now we want to do the conversion from this for this particular point in the camera frame. So camera, as you know, is oriented like this, and it's a little on the top of the LiDAR in the z direction. So let's see how it is, and then we will see if the result makes sense. So the same way we get the LiDAR in camera by taking the inverse of the camera in LiDAR, and then we multiply the homogeneous version of the point to get with the LiDAR in camera transform to get the point in the camera frame, and comes out to be 1, minus 2, and 2. So let's see if this makes any sense or not. So this is this was your LiDAR frame, and the point was here, 1, 2, 3, and now the camera is here. So first of all, x stays the same because x is pointing the same direction as same height, so x stays the same, so that is 1. For y, before the y was here, which was 2, but now for camera the y is pointing downwards. So essentially your z becomes y now, which was 3 before, but because y is downwards, this would become minus 3, but also you've shifted the camera 1 by 1 meter up, so this becomes minus 2. And then for the z, basically your your y before becomes z now, so y was 2, and now the z remains 2. So 1 minus 2, 2 is the output. I know this can get a little confusing when doing the transforms, but once you get a hang of it and you know how to implement it, then you can do, like, for a series of say 100,000 points, you can just do the simple mathematics, and it in code it would rapidly right away make the transforms for you. It would transform coordinates. So that's it for this video, guys. In this video I wanted to show you how to do the coordinate transforms from one coordinate frame to the other, how to get the transformation matrices, and also then how to transform say XYZ points from one frame to the other. Through this video, I hope you were able to get some understanding of coordinate transforms in computer vision and robotics. If you like this video, please hit the like button, subscribe to the channel, and hit the bell icon so you are notified about any new video that we upload. Thanks a lot for watching, guys, and I'll see you in the next video.